So in conclusion, it's an extremely difficult product to get right. And the point is that it's at the confluence of all these difficult requirements. Extremely high efficiency, very low cost, really high reliability, very long lifetime, critical robustness. I mean, everything is difficult to achieve. You can do any one of these issues one by one, it'd be okay. When you put everything together, it becomes a really difficult problem to solve. But, you know, it's worth it, so that's why we did it. All right, that concludes this presentation. I'd definitely take some questions if there are any. And thank you. Thank you.
So you said that you, in your predictive control, you only have the input of the voltage balance of input and output,
and the desired current.
Correct.
Yeah.
Don't you need to know the frequency also?
No, because I look at it on a microsecond by microsecond base, right? So the frequency is built in the current I want to get out, right? In my system, I build an image of the current I want to push out. So at every point in time, I say, well, what is the current I want now? Okay, you see what I mean? The current happens to be, of course, a sine wave, which is synchronized with the grid voltage, but this is independent from the power control.
So you don't have any idea on how much current is currently going on in the line, on the grid?
Correct.
You just work on voltages.
Yeah, well, yes, yeah. Yes, absolutely true.
So does it make me, so if there is already a high current running on the line, and then does it make a difference if you try to inject more current? Or
no, well, I want to say current is the current that the unit itself produces, right? I don't know, nor I care to know what's actually going on between the grid and the house, right? That's going by, it's none of my business really, right? What I care to know, what I care to do is know what current, or generate the right current that is I inject on grid, right? So, and I do that every microsecond, I do that. Does that make sense? Okay. Uh-huh.
So you mentioned that when you're using existing technologies, you can't hit the limit in power line communication and get 6 devices on there.
On that one system we're looking at, yeah.
System, yeah.
Uh-huh.
What problems were you getting? Was it like?
So I'm not going to give any names, but it was a standard product that was compliant to a standard called HPA 1.0. That's fairly old now, but and it was a OFDM-based transmission system, orthogonal frequency division multiplex. And the problem they had in that system is that they had to transmit a lot of energy across the band, okay? But they were also constrained by the noise floor of the power line of the AC, you know, in that band, of course. So they had to inject quite a bit of power to be above the noise floor that they expected. So the problem I had is that each of my microinverters were actually compliant, but the more you add, the more the noise floor goes up, right? And they didn't expect that. So it was working fine at night, but not during the day, which is a little bit of an issue because that's when you want the data. So we had to get away from that noise floor issue. And so we couldn't use that technology whatsoever. We had to go do something entirely different.
So I can see why that would be an issue on the AC ones. Out of curiosity, if it was DC, would you have the same issues? If you had DC line.
So on a DC line, there is no standard for emission. So basically, it's a system approach. You have to say, well, what noise is a converter going to produce on the line, or any other equipment for that matter, right?
I see. Oh, I see. So you guys were breaking the standard.
Well, no, we were fine with the standard. Each unit was standard compliant, but the system analysis was totally faulty. Okay. Yeah, I would have had to increase my power transmission, you know, my transmitted power to be able to keep up with the noise floor that was rising, right? So we just couldn't do that. What type of failures we see? So we have very good failure rates, excellent failure rates, but of course we do see, you know. I'm not sure I understand, I'm sorry. What fails the most? I don't have a good answer for this. You know, we have about 300 parts in there. Sometimes we have, that box is potted, by the way, it's filled with polyurethane compound. You have a variety of different failures. It's not one single component that fails more than others. Sometimes you have solder joint breaking. That's one of the most common problems. And it's not really dependent on the part itself. Sometimes you have wire breaking in a transformer. I mean, small events, right? And by the way, we have a very, very sophisticated product verification cycle. It takes between 3 and 6 months to verify the product is deemed, you know, sellable. And we find, you know, sometimes you change some very small things, and all of a sudden things start going bad. We had a problem not long ago. It was just on a resistor, and the resistor was changing. The value was changing over time, and you will bake it to 85C for a while, and it will go back. But there is some bizarre problems you never expect to see on a stupid resistor, and. And you know, so you have to chase them all. It's amazing. I mean, when you have to get to below 0.1% of return rate, which we are at basically right now, everything matters. You have to treat every part with the same amount of scrutiny. You know, it's very, very. You have to know exactly what's going on at every location. Yet again, whether it's mechanical stress, whether it's corrosion, whether it's chemical compatibility, whether it's electrical, of course, power, current, voltage, whatever, you have to know exactly what's going on at every part and every interface at every joint, at every, you know, material, you know, joint, right? So it's tough. Uh-huh. Uh-huh. A lot of yelling in a room. No. The issue is that the module vendors warranties a product for 25 years, and it's really misleading because what they warranty is that the power production, you know, all PV modules degrade over time, right? And really what they warranty is that the degradation should be more than whatever, you know, 10%, depending on the vendor, over 25 years. So problem is that they don't warranty that the junction box fell off the back of the module. They don't warranty that the frame fell apart. They don't warranty that the backsheet fell apart, you know, open up from the back of the module. They don't warranty none of that stuff. But when you start, you have to show you're better than anybody else, and that's kind of what led to that, you know, very difficult decision. Actually, it didn't go easy. Uh-huh.
So how did you do your accelerated lifetime testing, given that you guys haven't been in business in 25 years?
So we have a very large building which is filled with chambers, with temperature chambers and humidity chambers, and we just cycle the heck out of them. A whole, you know, it takes 3 months to do that. We have 3 different type of tests, actually 4, and we just operate the unit at full power, 85 C ambient, and do, you know, under high humidity conditions, and that's one test for 2,000 hours, I believe it is, and then another one we just go up and down in temperature very fast, and we try to accelerate our failures that way. We find, you know, a lot of stuff this way. It's very good. It's a very difficult science, that, because you need to, in order to do that properly, you really need to understand what the failure modes are. You have to know, it's kind of, before you have a failure, you need to know what the failure mode is so you can design the test properly, right? So there's a little bit of chicken and egg problem in there. But by doing what you're doing, you can get really close to, and we've got pretty good correlation between the failures we get in that test versus failure we get in the field. Uh-huh. Go for it.
What's your targeting the big solar farm or residential?
No, mostly residential. Okay, we work well in small, very competitive and very small, in smaller systems. So, I mean, we have large market shares all over, in some locations more than others. Hawaii, we do very well. But yeah, we mostly stay in the, let's say, sub 50 kilowatt range, which doesn't mean that we don't have large scale projects. We have many projects in the 500 kilowatt to megawatt range. So those consumes 2,000 inverters in one shot.
The other question is, when you think about like solar farm, when you think about using microinverter, one of the things you think is that you can't eliminate the effect of shading.
Sure.
So in terms of big solar farm,
It doesn't really happen. Yeah.
yeah. So what's the benefit?
So the benefit there is not, I mean, that's not the way you market your product in solar farm. In solar farm, you market your product by the fact that if the inverter goes bad, you don't go down for 2 weeks, right? We talked, of course, to big developers and it's called EPC engineering and something consultants. And what on big inverters, on megawatt inverters, they lose that inverter in average every year. And when it goes bad, you don't go and muck with it. You go get the maintenance people, and you have to fly them in typically, and it takes a while. So system availability is the name of the game there, and that works really, really well.
So you mentioned that it's really hard to discover on your island, and it seems like it's even harder because let's say you're not just one solar panel, you have like all the other ones. You have to be really sensitive to check like when my other 50 kilowatts are still on. Do you like talk amongst yourselves?
So we actually synchronize all the units. So whatever disturbance we do it all of them at the same time. So it totally scales, right? If everything was if that process was totally randomized across unit, it will never work actually. It will pass the standard, mind you, but it will not work in reality. Okay, so but we synchronize all the units so they do the disturbance exactly at the same time. So it linearly scales. So DC-DC converters, yes. So that concept is, but no, actually it's newer than the microinverter because microinverter started in mid 90s actually. The concept of it. So some people indeed do the MPPT at the DC-DC converter level. So they have one DC-DC converter per unit. Let's say you get 30 volt in, 8 amps, you'll get 25 volt out, 10 amps, okay, or something like that. And the MPPT is down there, and the inverter now only does the DC to AC conversion, right? So my point of view on there, but I'm certainly biased, is that the only reason you will do this is because you don't know how to do a microinverter. But because the truth of the matter is that the string inverter is really what you want to eliminate, and it's still there. So sure, you can do conversion on a DC-DC point, and it's not very expensive, but you still have the string inverter which is still there, so you don't have any of the advantage. You still have high voltage DC, you still have single point of failure, you still have all that stuff that are all the, you still have the safety issue. It's always there. So it's really not solving the problem I think we should be solving. So we work, we have limited resources, of course. So we work for the bulk of the market, right? And right now, the bulk of the market in 60-cell silicon module. So that's over 99% of our cells are in there. We can work with any type of module as long as the voltage and power range are in the ballpark, right? We looked a lot in 2008 and 9 to work with other module technologies, but the problem there it's all over the place. You have voltages running from 40 volt to 300 volt. You have power going from 70 watt to 500 watt back then. So it becomes really tough to make a product which can address most of that. Actually, it's impossible. So we had, and it turned out that the market converged to silicon anyway. So that solved the problem for us. We could do something. It's just you need to invest your effort into something which you're going to sell. If you don't sell it, there's no point. or not enough. Thank you.